Hello, this is Nicholas, and I want to talk about one more type of differential equation to get in our tool bag, and this is equations of the type alpha x plus beta y plus gamma dx plus ax plus by plus c dy equals 0. So basically just two lines in standard form multiplied by the differentials dx and dy. Now, first of all, I want to just notice that if this gamma, which is a constant, and this c, which is a constant, if those weren't there, if we could somehow get rid of those constants, then the resulting equation, just alpha x plus beta y and ax plus by, that would be homogeneous, right? Homogeneous for degree n equals 1. So the goal, it would seem, would be to get rid of these constants here. And there is a relatively easy way to do that. The idea is these lines, they intersect at a point. We're assuming they intersect at a point. If they don't intersect at a point, then the equation becomes really trivial, right? Then one is just a scalar multiple of the other, and so the whole thing is just separable. But we assume that they intersect at a point. So then if they intersect at a point, see if we've got our x, our y. Oh, I still have the thing on. So our x-axis, the y-axis, and this is the origin. And this and this line here. And this is, say, alpha x plus beta y equals gamma. And this is ax plus by equals c. So they intersect at a point, and this is the point. If we can, and let's call this point h comma k. If we translate our coordinate axes so that, let's call them new axes. Let's say that now the lines are on the, are on the, call it the u and the v axes, then where they intersect will be 0, right? C would be equal to 0 and gamma would be equal to 0. If we translate our axes, right? Because here on the new axis, x is 0 and y is 0, so a times 0 plus b times 0 equals 0, so c would be 0, and alpha times 0 plus beta times 0 would be equal to 0, and then that would mean gamma would be equal to 0. So if we can just translate our axes so that the origin is where the two lines intersect, then the constants have to go away. And so we can just introduce a substitution. We can just have x equal to u, the new x-axis, plus h, the x-coordinate of the intersection of the two lines, and y be equal to v plus k, the new y-axis plus the intersection of the y-coordinate of the intersection of the two lines. And if we started with v, and we see, because this whole distance here, say this whole distance here up to this point here, that distance there is k from, I'll draw a little bit over, from the origin to here. This distance here is k. And so if we were to subtract k distance from v, then it would bring it back over to here, right? Likewise, if we were to subtract the same thing along the x-axis, it would get brought back to the origin, and so this is a valid transformation. So this is the general idea. We can just substitute this in to where the two lines intersect, and then the resulting equation will be homogeneous, and we know how to solve those. So as an example, 2x plus y plus 4 dx plus x minus 2y minus 2 dy is equal to 0. So we just want to find where c and gamma are equal to 0. So we get that we let h become k because we want to find the intersection of the two lines, which is the point h comma k. So we get the equation 2h plus k plus 4. That's going to be equal to 0. That's going to be our new that's going to be our new origin of our translated axes. And then h minus 2k minus 2 is equal to 0. And so now we just need to solve for h and k. So 2h minus 4k minus 4 is equal to 0. Subtract these two, that goes away. 5k plus 8 is equal to 0. So k is negative 8/5. And we can solve for h. And so 2h minus 8/5. Well, 8/5 plus 4, it's minus 8/5 plus, what's 4 20/5 equals 0. So 2h plus 12/5 is equal to 0. H is equal to negative 6/5. So now if we do the substitution, if we let x equal u, the new x-axis, minus 6/5, and y, be equal to v, the new y-axis, minus 8/5, then it is guaranteed that we will have no constant terms. In other words, I don't even have to plug in, I don't have to plug in x to be u minus 6/5 and then distribute that with the u and distribute that with the 6/5 and then add that to the v minus 8/5. I know right off the bat from the way I set up my equations that it has to be that I get 2u plus v dx plus u minus 2v, that's 2v, dy, I use dx, this should be, the u it's du because we're on the new x-axis, and this should be dv because we're on the new y-axis, and that's equal to 0. And now that equation is homogeneous, right? So I guess I maybe should do, traditionally you use v in the homogeneous solution, so I'll have to use a different variable. You could do the substitution u is equal to wv, or v is equal to wu, it doesn't really matter which one. And then you could get a separable equation that you could solve. Once you solve that separable equation, you'd back substitute for these, whichever one you used, and then you'd have to back substitute for this and for this. So I know we've done homogeneous equations, and I know you know how to back substitute. So once I get to this point, I'm really going to say that I'm done, because solving homogeneous equations is done, and solving separable equations is done, and back substitution is an algebra thing. So at this particular point, I would just like to emphasize that the translation of axes. So one thing, when you go to back substitute, we're now in terms of u. So now u would be x plus 6/5. That's what I was trying to say earlier, where if I took u and I added if I took a point x, say I took a point x here and I added 6/5 to it, I would be at u. I would be on the u-axis. And so likewise, if I took that point x, or if I was on the u-axis already and then I subtract 6/5 from it, I'll be on the on the x-axis. And so that's the relation between the two. that's why these transformations work. And likewise, v would be, keep mixing it up. When you get v, just replace every v with y plus 8/5, and every u with